Every impulse question that we've seen over the last couple of days have involved a single object. That object experienced a gain of momentum or a loss of momentum. Today what I want to do is look at a situation where we have two objects in the same problem. We want to analyze that. Like up until now, it's been the ball falling. What's the impulse experienced by the ball as it falls? Or what's the impulse experienced by the ball as it stops when it hits the ground? Or what's the impulse experienced by the car as it slows down? Single object, right? What if two cars collide with each other? What if you get car A and car B colliding with each other? How do we look at the impulse there? Well, I'm going to start a sentence. I want you to finish it for me. Okay? I feel like our relationship has come to the point where you can finish my sentences now. Okay? Finish my sentence. If object A experiences a certain impulse when it collides with object B, then object B will experience an equal and opposite impulse. So if you have two cars colliding, car A and car B collide, and car A experiences an impulse of, let's say, 12,000, car B will experience an impulse of negative 12,000. The impulse experienced by two objects will always be equal in magnitude and opposite in direction. Now, I put a little note at the bottom here. It says, this is independent or regardless of the masses or velocities involved. I don't know if you guys remember this, but last year in Physics 20, regardless of whose class you were in, you got a multiple choice question on your dynamics test that asked you to compare the forces involved when a bug hit a windshield. Do you guys remember that question? How did the force on the bug compare to the force on the car? They were equal and opposite. Despite the fact that the bug was way less massive than the car, the forces were equal and opposite. Guess what? The impulse is too. If the bug experienced an impulse of -2, then guess what the car experienced? It experienced an impulse of +2. It doesn't matter that one is way heavier than the other. What if car A is moving at 10 meters per second, car B is moving at 30 meters per second? Doesn't matter. Car A will experience a certain impulse, car B will experience an equal and opposite impulse. Always, zero exceptions. So when we have two objects colliding, regardless of mass, regardless of speed, one object will experience a certain impulse, the other object will experience always an equal and opposite impulse. It's real similar to Newton's third law, right? Object A applies a force on object B applies an equal and opposite force on object A. We're going to do an example in a minute involving two objects. Before we do that, though, I want to point out something that's really, really important. When you've got two objects, two vehicles, two cars, for instance, you've got data for car A and car B. What I want you to make sure that you do is focus on one of them. In other words, treat it like the problems that you've already done. Just because there's two objects doesn't mean it changes the problem. When we had the one car slowing down, we use data for that one car. If we have two cars colliding, use data for car A or for car B, but not for both of them. Does that make sense? Pick a car and go with the car. Pick a car, any car, and go with that car. So if you're analyzing a problem like this involving two objects or more objects using impulse, use data for one of the objects or the other, but not for both. Let's take a look at that example. This is on your example sheet that I handed out on the first day, by the way. So copy out the solution, but not the question, all right? 1,200 kilogram car traveling north at 10 collides with a 1,000 kilogram car traveling south at 10. We're going to circle that to remind us that we've got a positive and a negative here. Two cars entangle. What does that mean? Entangle. They like stick together, right? Stick together, become one object, and they both head off at a velocity of 0.901 to the north immediately after the collision. Lasts for 0.08 seconds. What's the force of impact on the light car? What's the force of impact on the heavier car? Okay, what do you got to do here? This is impulse. Impulse, we know that because we have force and time. Remember back on our always list here, force and time gives us impulse. Pick a car, any car. Which car do you want to deal with, the light car or the heavy car? Doesn't really matter. Which one do you want to do? the light car, the 1,000 kilogram car? We can do that. Okay, if we look at the light car and we write down the data for that, we would say the mass is 1,000 kilograms. We would say the initial velocity is negative 10 meters per second because it's to the south, right? We would say the final velocity after it collides and entangles is 0.901 meters per second. And we would say the time of impact is 0.080 seconds. Looking for the force, let's say F times delta T is equal to M times delta V. Let's use the mass of the little car, the light one, 1,000 kilograms, times delta V. Careful on this, 0.901 minus negative 10. 0.901 subtract negative 10, which ends up being the same thing as adding. Divide that by 0.080 seconds. You do the math there, works out to be 1.36 times 10 to the 5 meters per second. Much more. There's the force on the light car. Okay, quick, lightning fast answer. What's the force on the heavy car?
Same.
Almost. Negative 1.36 times 10 to the 5. What would have happened if we had to use data for the heavier car? We would have gotten negative 1.36. We know the impulse is the same but opposite. We also know the force is the same but opposite.